So welcome to the second lecture of economic integration, European economic integration. This the topic of today's lecture is integration by way of economic growth. So I'd like to get started by reviewing last time. This is a traditional way of doing things in my class. We'll then talk about the Solow model of economic growth. Excuse me for a second. So the Solow model of economic growth is a way of understanding why economies grow over time. And one way of understanding the long-run consequences of European integration is observing the growth of standards of living and productivity across regions or across countries. And economists are trying to understand this process. Their writ is actually to figure out ways of compactly modeling this development. One of the most important things that we come up with in this course, or that Robert Solow came up with 50 plus years ago, was that countries that have the same basic technology, the same rule of law, the same institutions, the same behavior of households will basically eventually converge to similar levels of GDP per capita, similar levels of standards of living. Now, of course, this model has lots of bells and whistles and lots of complications, but in general, this is a very robust prediction of this model. Countries that are underdeveloped, given access to technology, given access to markets, will eventually develop and rise to the rate of the leading or the frontier economy. In this case, the most productive economies of the European Union or the United States or Japan. It turns out that this convergence does occur, but it occurs at a fairly slow rate. The unconditional expectation is that this rate of convergence is about 2% empirically. That's pretty slow. So we'll have to just understand what that implies. Are there ways to do better? Yes. European integration relies not only on bootstrap economic growth from within, but also importing capital and exporting labor. So we'll talk about those things as well. I'll give you some applications of this model to regional integration in non-European contexts. We'll talk about the United States and Japan, and we'll talk about Europe. We'll talk about Germany after unification. And also speak of some limitations of the Solow model in the very end of the class. Okay? So last time, we asked the question, what is European integration? We discussed real versus monetary issues. I gave you macroeconomic and microeconomic perspectives on this issue. I also talked about positive analysis versus normative analysis. In economics, we're mostly concerned with positive analysis, understanding the world as it is, and only after that, perhaps making an informed judgment and bringing our own opinion into the game. We talked about economic history. I gave you a little bit of a rather verbal history lesson, probably not news for most of you, but just to get the groundwork done, we have to understand where Europe came from. It came from two very disastrous wars, the second of which led to tens of millions of deaths and destruction of the capital stock, leading to some countries to be thrown back in development several decades. The question is, Europe wanted to avoid this happening again. And the fundamental idea behind the European Union and even the monetary union is that economic integration can actually bring about political integration, if not even peaceful coexistence. I'll talk about these two definitions again because it's very important. Okay? We're going to talk about the efficiency criterion, which is like economists like to talk about. How do we reach the most efficient point on the frontier? There's always considered a trade-off between various ways of raising economic growth, costs human resources, costs labor. Still in all, we can unify or put 2 or 3 or 4 regions together and see what they can do, given their endowments of capital and labor. So the efficient frontier of the production patterns they can achieve is really kind of our, gold standard. We'd like to reach that, and the question is, can we do that? And obviously, not all countries can at any point in time. So how to do that is what we'd call the efficiency criterion. In particular, can I use the Pareto criterion? Can I make individuals in one region or country better off without making the others worse off? And that's the promise, of course, of many attributes of integration, one of which, of course, is trade, but also migration of labor and capital. You might take a different position, which tends to be more political, tends to be more normative. You might feel that it's very important to have some sort of level of equality in society, equality of outcomes, probably more likely equality of opportunity, but in any case, it's a different set of criteria. It involves already a bit of a value judgment. There's nothing wrong with that. There might be a trade-off between efficiency and fairness. We see that in this country, and we see that in the United States, so it's worth talking about. Those are very important dimensions of European economic integration, important dimensions of any integration episode. You have winners and losers. You know, we gain from trade with the Far East. We have cheaper goods, but some of our workers may lose their jobs. There might be, and there most likely are, ways of compensating the losers, retraining them, moving them into other areas where they're more productive and efficient. And this is a decision that society has to make. In general, economists tend to go for the Pareto type of approach and try to figure out some compensation principle. Okay, we talked about the Edgeworth-Box. Again, this is review for those who didn't come last time, as a way of describing the allocation of factors that are essential, again, for our well-being. To have a high GDP or GNI per capita that you have in this country or in France or in Great Britain, you need to have capital and labor in use. You also need to have a production function, a means of transforming those inputs into things that we like to consume, to use, or need. That production function is a key assumption in our work. So we've thought about an example of how to decide how to allocate production factors across two regions, first as an endowment, and the question is, what can we do with that endowment? And we took the example of Poland and Finland as a metaphor for East-West European integration, could also be a metaphor for East-West German integration after 1990. It can be used in many contexts. Again, the assumption that you should know as bachelor students is all the stuff that goes into the assumption, which is not exactly concealed, of a constant returns production function. And most importantly, that both regions that are using the labor and capital in this Edgeworth-Box applied to factor allocations is the same. Okay, so we're kind of ruling out ex ante differences in technology that are durable and last for a long, long time. This is an important assumption. We'll come back to it later. Okay, it's well known that even if you gave Niger or Nigeria the same capital per capita that the United States has, you gave it the same human capital, education, attainment that the US has, you would still not reach anywhere close the level of GDP per capita that is observed in the United States. In fact, the most recent estimate in a paper published now more than 10 years ago was that the factor is by a factor of 7. Okay, so there's something else out there. The production functions are different. So implicitly assumed in this Edgeworth-Box is that both Finland and Poland have the same access to the same production function, the same technology of transforming capital and labor into output. If you don't go for that, then you're going to have a different type of Edgeworth-Box. You're going to have a different set of efficiency criteria. You'll have to work a little bit harder. But the presumption is a free exchange of information, perhaps also political influence, will level out the playing field, at least in the European context. It is a fact that levels of corruption and mismanagement that are observed in some parts of Europe have decreased since these countries joined the EU. It's part of the European Charter. The chapters of the European Treaty basically include, or the acquis communautaire, include provisions to give transparency and rule of law a very high position in the pecking order of things that have to be done. Okay, so people can complain and joke about parts of southeastern Europe, but it's gotten a lot better in the past 20 years than it was before. So remember that. That's a very important point that will show up on an exam for sure. Constant returns. What does that mean? What does that imply for the marginal products of labor and capital? What does it imply for the consequences of doubling the inputs of both factors? Okay? So here's the picture again for your viewing pleasure. The endowment is point E, and implicit in this idea is that Finland has a significantly higher capital-labor ratio, okay, which is given by the angle that EO makes with the horizontal axis, okay, as compared to Poland, which is OE from the other end, okay? So that's the initial condition. And that will determine, in a competitive economy, factor remunerations. It will affect the incentives of capital and labor to move. It will affect the incentives of firms to invest. And it will affect also, in a more general economy, the incentive of workers to work or not. Okay, so we'll talk about that's part of the course. We talked about 4 mechanisms. Today we're going to speak about the first one, but I'll run through them again. Many of you didn't come last time, so here they are again. Economic growth. We're going to be talking about extending the level of this Edgeworth-Box, the height of it, if you will. And we're going to talk about it as an internal mechanism inside of Poland. So this is basically Polish citizens deferring consumption, households not eating, and at the cost of building something, building a house, installing a piece of machinery, buying a truck, okay, means of production. You can also think of Finns actually just moving capital. You can also think of Poles moving to Finland, and you can think of trade in goods in a certain sense that will be made clear in 4 lectures. All these are different mechanisms that in some sense are substitutes for one another, but they have different time horizons. And understanding that is understanding the pressure on politicians to do things, to accelerate or even decelerate, slow down integration processes. Let's focus on this one. To do this, I'm going to review some theory that most of you have seen, but it's probably not in this detail and perhaps not in this level of application. And then I'm going to derive some implications of those theories, or this particular theory, which is actually a whole sequence of theories that involve trying to predict why nations grow and why nations don't. Okay, so this is an absolute essential part of your toolkit as an economist with a bachelor degree coming from this university. So if you're frustrated because you've never seen it, then it's a good idea to attend the section and listen to what Grzegorz has to say about it. Okay? I'm talking about the Solow model of economic growth. Robert Solow wrote these seminal papers in 1956 and 57. An Australian by the name of Swan also produced a similar paper. There's some rivalry between the two, although they're both very old. I think Swan actually has passed away. Solow's a very old man now. This is the central aspect of growth theory. It's also a central part of macroeconomics, understanding the long run, the low frequency movements of output per capita, capital and investment. It's going to give us a tool that we can use comparative statics to study. We're going to talk about what happens when key parameters in this model change. Now again, this is an applied economics course. This is not high-level theory. If you want to do that, take a master's degree and come to my Introduction to Advanced Macroeconomics. We can talk about that. This is about trying to apply intelligently lowbrow theory. So the exam questions you'll see, the questions we'll talk about in the section, involve using this theory in a creative and constructive way to help us organize our thinking about these episodes. Okay? So we'll start by making an assumption. We're going to assume that in these two regions, for the sake of the argument, that labor is fully employed. You can deviate from this trivially, but it raises the level of complexity by quite a bit. So we want to start with this assumption and work from there. That's the way economists do. It's the application of Occam's razor. Simplify and then conquer. Okay, so understand this model and you'll be in good shape for the next step. So we'll basically use some symbols. We'll assume that N represents the number of people in a region, or the integrated region described by the Edgeworth-Box. We're going to assume that each person has the potential of working H hours in employment. Now what really goes into the production function is not N. It's not H. It's actually L, employment. Okay, so a full employment assumption would be imposing that L equals N for the sake of the argument. Believe me, there are ways to change this. And there are ways to do this that are quite interesting, but they don't change the underlying logic of the Solow model. Solow model with unemployment works just like the Solow model with unemployment. It's just a way of getting the model in a reasonable representation. We talk about the diagram, the Solow diagram, which will come up in a second. So we're going to assume full employment. Okay, we're going to assume that people work H hours, and therefore we're just going to normalize this. So we'll be talking interchangeably about capita, people, and workers. Doesn't mean that I don't believe there's a difference. It's just a means of making the argument simpler. Okay? So later on we can talk about ways, and we will talk about ways of mobilizing labor. Those turn out to be important, but not a long-term source of economic growth. So one of the reasons Germany has grown a lot in the past 10 years is because the Hartz reforms were successful in getting people in work. You can't do that forever. You can't have Hartz reforms every day. It leads to a level effect and not a growth effect. And I'm interested in growth effects in this model. Okay, it doesn't mean it's unimportant. So if I can get women to join the labor force, like Sweden has, or Norway has, or in the recent years Germany has, this is a source of short-run growth, moving from one level of GDP per capita to another, because you're getting more people per capita in work. Okay? You can also change H. So over time we observe that there's an income and a substitution effect. Over time the income effect dominates. People tend to want to work less, fewer hours, and there's nothing wrong with that. 100 years ago people were working maybe 20, 30, 40% longer work weeks than we are today. It was unheard of not to work on Saturday. Okay, so this is a part of the model as well, but we're going to freeze that out of the picture. So here's the math that we need to think about this. We start with a simple production of two factors. K is a stock. It's the sum of all the undepreciated increments to the capital stock since the beginning of time. So this building is kind of part of the German capital stock. It was built in 1905. It's been renovated, and it's still productive. This microphone is probably from the GDR days. It's also still working, still useful means of production. All those storefronts out there, that's the capital stock we'll be talking about. Labor is the labor input I described already. Again, this is a model about economic growth and how nations, regions accumulate capital and why they do so. So all that I'm going to proceed to talk about is about the means of production, the mechanism of production. We call that a production function. It's just an abstraction of the way economies convert labor and capital into goods that are useful, provide utility, or can also be invested in future production. It gives rise to Marx's idea of the reproducible economic system. Okay? So if you believe in a production function, if you're willing to make that assumption, in fact, you can make it a little bit less rigorous by adding A as a labor augmenting component. So think of this as basically the effectiveness, which is exogenous, of an hour's worth of labor as a technological exogenously given factor. Then we have what we call a constant returns to scale production function with Herod-neutral technical change. A can grow over time. Right now I'll set A equals to 1, and then we'll finish the hour talking about growing A. So we want to have a production function that has neoclassical properties. That means that for the aggregate economy, adding an extra unit of labor brings something to the table. It increases output, but at a diminishing rate. That's a key assumption of neoclassical economics. Okay? You can also have increasing returns to inputs, increasing marginal product. But those types of economies tend to have very strange behavior that we don't observe in the real world. Okay? We'll assume constant returns to scale, which means, as I said before, double everything, you double output. Holding A constant if A is not equal to 1. If you allow me to do that, I can write an intensive form of the production function, which is simply a function of the capital labor or capital per capita variable. All I've done here is divide by L, and a constant returns function says if you divide or multiply by a positive number, you just scale up or scale down that number. So what we've done basically is create an intensive version of the production function, which is only a function of capital intensity. Now you might say, well, so what? This step has already created an amazing ability for you to account for differences across European countries where technology is comparable, where rule of law is comparable. Okay? It helps us explain why East Germany was less productive before the wall came down, because capital per capita in East Germany was about a fourth, possibly even less, at market prices. Okay, so one of the most important things you needed to do to integrate East Germany into the world economy was to bring physical capital from outside or from inside. Okay? Now, little f is the intensive version of this production function. It inherits the properties of the big F in the sense that it's concave. So the marginal product of capital per capita is positive, but at a declining rate. The second derivative of little f with respect to little k is negative. That's absolutely essential for the neoclassical theory of growth. This is a diagram of that relationship. Okay? So you get the concavity of the production function in the fact that the slope of f at any point is decreasing in little k. It's an important trait that will come up in a second. Okay, so on the horizontal, I've got the capital per capita as promised, and we've got output per capita at the top. So already we've identified an important source, not necessarily the most important source, of standards of living being different. And if you have the same technology, it is, as we stand here, is probably the only source of difference. Okay, so putting it differently, one of the reasons why Germany produces more per capita than Slovenia, although the Slovenes are pretty well-educated people, they have pretty good production technology. They just copy what the Germans have done, or the Germans may even have invested there. The difference is they don't have capital yet. So the question is, if they're going to converge to German standards of living, they're going to have to accumulate capital. Ceteris paribus. Okay, so how do they do that? Well, if you allow me that conclusion, we already know that capital doesn't come from the sky. It doesn't come from some big brother in general. It usually comes, if you're an autarkic country, it comes from your own pocket. You have to give up something. You have to literally forsake consumption to have goods that you can use in the production process. Now, I'm sure all of you are convinced of that, but I'll give you an example anyway. This building belonged to the Industrie- und Handelskammer. Okay? It basically was the training business school, the business school when it was first founded. Okay? There were many people that wanted to buy this building after the wall came down and convert it into a big hotel. Okay? Now you can see that those are different uses in production of the same capital good. One could even imagine converting this into a set of apartments. This could be a huge loft. We could all live in here, together, have little bunk beds. There's a trade-off between consumption and investment. Okay? It's an abstraction, obviously. There's putty clay aspects. But in the end, a car that you use for personal use can also be used for business use. A computer you use for personal use can also be used for business use. And if you have a technology that cannot be adapted completely, you can always let the machine depreciate and use the depreciated fund to do something else. Okay, to put it in German, du kannst immer von der Substanz leben, solange es Substanz gibt. So as long as there's something to depreciate and eat up, you can do it. So in the abstract world of economics, we're going to basically consider that capital to be fungible in uses of consumption and investment. It's just an abstraction, but it's a pretty good one. And you can see that countries that literally run themselves into the ground by not investing are doing exactly what I just described. Put differently, a country like China with an investment rate of 40% of GDP is accumulating a lot of capital. And I'm talking not just about machines, I'm talking about highways, airports, mass transit. Even pollution abatement could be considered investment. Okay, so what determines where an economy lands on this picture, right? This is the interesting question. What gives us K? Okay, it has to be the sum of a lot of decisions in the past, because capital is a stock variable. The present value of capital represents the undepreciated increments of the past. So it's a race between gross investment We call that I. It appears in the GDP accounts. And depreciation. Okay, depreciation means that literally this building over 100 years will look very different if you don't do something with it. And I came here in 1993, and this building did look a lot different. Okay, so depreciation is a fact. It means literally you have to keep investing just to stand still. Right? So where does the K come from? In the Solow model, as in all models, the reality is the households ultimately do the saving. Even if you think the firms are doing the saving because they're retaining earnings, somebody owns those firms. Households own those firms. Firms are not people. People own the firms. They may be very wealthy individuals, but that doesn't get you around the logic that there's a household that owns the firm and can defer consumption or consume. So in a closed economy without any government, we have the fundamental identity or the equality. It's not an identity, it's an equilibrium condition that the investment that's used has to be saved by the households. And households save out of income. There's no government, there's no taxes in this very simple version of the Solow model. Therefore, it's just the savings rate times income, which is GDP. In a closed economy, GDP is equal to GNI, so that is income. Okay, these are all basic macroeconomic facts. If you don't know them, you should learn them because it's essential. S is an exogenous rate. So S is a number like 0.15 in the United States. It's not household savings, it's household plus firm savings. Okay, so if Microsoft saves a lot of their profit and don't pay it out as dividend, then indeed they're saving on behalf of their owners. In Germany, the households do most of the saving. What's important for the economy is what both do. Okay, so again, using the same notation, we can take the identity of savings equals investment and just write savings as a fraction of GDP per capita. When I divide both left and right by the number of people, is going to give me S times my little production function, which I've called the intensive production function, F. Okay, so this is my savings equation. This is my savings function. It's a very mechanistic, but actually a fairly robust function in the sense that S does change. It's rising a little bit in the United States. It's always been very low. But again, if you include the firms, it's actually higher than you think. And in Germany, the households do most of the savings, firms tend to do less. Okay, so multiplying S less than 1 greater than 0 with this little f production function will give rise to this savings function. So we've already got one behavioral equation in our Solow model, which is this concave, equally concave, similarly concave savings function. So an additional unit of capital will lead to more saving, but less at the margin. It inherits the property of the production function. Okay, so already we can read off of that in an economy without a government. You can read off savings per capita, that's also investment per capita, and the residual is actually the most important thing that makes us happy is consumption. Right? We don't produce so we can buy capital goods and be proud of these shiny machines. That's not the existence that we call economic existence. We want to raise standards of living by giving people more consumption per capita. It doesn't mean necessarily driving cars, it means having health care, having services for old people, daycare. Government consumption can also fall under the rubric of consumption. Okay? All right, so that's the first part. We still have to get the other part of the scissors. What's going to determine where we land? We still haven't said how we get to K. Okay? So one presumption would be to think about the dynamics of the capital stock as a starting point. Namely, how much savings do I need to maintain any arbitrary level of capital on the horizontal axis? Okay, so to understand that, you need to understand what capital does. Capital literally depreciates. Okay, so the car you bought last year is worth less on the market, but also in terms of its value, its real economic value. If you buy a truck and use it for 5 years, it's not as productive.
not as useful. It's probably also obsolete. The same is true of software, which is also a part of investment, by the way. This computer is already obsolete. It's only a couple of years old. Technology moves on. Okay, so all these things contribute to depreciation of the capital stock. So we have to measure the net change and ask when the net change is equal to 0. That will give us a resting point along the horizontal axis. So we're going to ask under which conditions can we expect stationarity or a stationary state in the capital stock per capita in our Solow model. Okay, so you really have to think, I mean, some people have not really grasped this. I see this from the exams that I look at. It's important to understand this. So when delta K is equal to 0, delta means change over a discrete period of time, then investment in the gross sense, in the GDP sense, I, is equal to the depreciation of the capital stock in place already, which is delta K. Delta is a rate of depreciation. You can also think of delta as being a vector of different depreciation rates, multiplying with a vector of capital stocks of different types. But the abstraction helps us get through that vector and the inner product. Okay, so we don't have to do that. Again, the Solow model for undergraduates, this is just fine. This is the so-called Goldsmith equation, the capital accumulation equation for an economy. You can write out delta K as KT plus 1 minus KT, and you can put KT on the other side. You can have an equation that you probably saw already in macroeconomics. It's the same idea. Okay, so our Solow question is, when does that delta K stop? But actually, that's not the right question. The right question is, when does little delta K stop? Because we're doing this in capita per capita. Capital per capita changes not just because of gross investment being greater than depreciation. It's also if the labor supply that's in work is growing faster or slower. Right? So you can have capital constant and capital per capita shrinking because the number of workers is growing. So in a growing economy where lots of people are coming online, you really have to invest just to stand still. That's called the warranted level of investment. It's an idea that goes back to the 1950s and Herod Domar and all these people. Okay? So to do this right, we have to take the capital accumulation equation and account for the fact that people in work may be changing. In this country, maybe not. I say that a bit ironically, but it's not true, actually. Because of the crisis in Southern Europe, Europeans are coming from the south to the north, and they're trying to find jobs and getting jobs in Germany. So they're actually contributing to population growth or employment growth in Germany. So you'd think, ceteris paribus, to keep little k still, you'd have to increase gross investment. This is a very important point. It'll come up later. Okay, so under what conditions can we expect little k to stop growing? Well, it's quite easy. Anyone knows that the ratio changes as a function of the growth rates of the denominator relative to the numerator. If the denominator is growing faster, the ratio falls. If the numerator is growing faster, the ratio rises. So the condition that we look for in the so-called capital deepening line or capital widening line is effectively that the rate of growth of the capital stock is sufficient to cover both depreciation and population growth. Little n is the growth rate of population. Think of it as a race between the stock of capital and the stock of labor that's employed. And when those are the same, then the ratio is stable. So that's going to give us the basis for the capital widening line, which I'm about to plot. It's very trivial. If you look at it, it just says investment per capita is associated with stable little k, capital per capita, when it's enough to cover the necessary depreciation and the necessary population growth that's built into the system. Okay? So if you have a high capital labor ratio, capital labor ratio at the beginning, you're going to need more investment just to cover, just to stay still, just to stand still and cover the necessary reduction that will follow because of depreciation and population growth. Okay? This is just a line. Okay, so effectively the Solow model is going to ask, when are these two curves going to lead to a consistent level of capital per capita? Under those conditions, the economy has reached a steady state and is not growing, nor is it shrinking. Okay? So we put those two together, and then that's what we get. We get an intersection. This is the point at which savings that households bring forth through the savings function is just covered by the investment required to keep capital stable at K star. Given that K star, we can feed it into the production function and read off the production function how much output is being produced in the economy per capita. This is an amazingly simple but effective way of understanding what's going on. Solow invented this in the 1950s, and it was a simple arbitrage of which no one else had thought about. Neoclassical production theory with growth theory. Okay, so the rest is history. We're all using this model and thinking about growth in these pictures. Okay, so you know, I've written down the essentials: savings, investment, behavior, equilibrium. Already we've got quite a bit of information here. Little k dot doesn't change at that equilibrium, even though the economy is growing, because the number of people is growing, number of people in work. So in this economy, in this simplified economy, equilibrium growth is equal to the rate of growth of population. That's not the end of the story. You can change it. I can add a lot of things. I will in a second. That's already quite a mouthful for people, especially people who just came in. It might be difficult to follow what I'm talking about. Okay? So let's do some analysis. Let's do some comparative statics. Let's ask what happens if one of these key parameters actually changes. Okay, this is the way economists like to think. We like to divide the world into simple exogenous causal factors and assert causality. It may be dangerous. You need to have better evidence to make the complete causal case. But we can still ask, if you think the Solow model is right, what are the deductive conclusions? What can I deduce from that model? So here's the first one. An increase in the savings rate from little s to little s prime. Okay? So what happens then? Well, obviously something's going to shift. Okay, and I know all of you have seen the Solow model, so I know you all know the answer, so I'm just going to tell you. Okay? The savings rate increasing leads to a shift in the savings function. It doesn't lead to a change in the production function. Okay, so the economy is basically deciding to allocate more of its given production at given capital stock per capita to the accumulation of capital. Okay, so that's already kind of maybe a painful decision, because it means that people currently alive are actually not able to enjoy that restaurant meal or that drive in the nice Ferrari. They're actually going to use those resources to produce more meals and more Ferraris in the future. Okay? So you already have a very interesting distributional issue. Young people, old people have different ideas about the desirability of doing that. And if you want to learn more about that, take a master's course in economics, in macroeconomics. Okay? But for us, important to see that at this level, a shift upward of the S prime, of the savings rate to S prime, shifts the savings function, which means that at this particular point, this implied savings of the households will exceed the capital required to keep that capital stock per capita constant. So that means we have capital accumulation. Delta K in that instant is going to be positive, and therefore the economy will start to move to the right. Okay? So the arrows in the diagram designate the direction. Movement along the production function as more capital is put to use. Think of China with its very, very high savings rate. Okay? This is kind of if you looked at China's savings rate in the 1990s, it was lower. So this is one way of understanding the Chinese miracle. One has to understand why the Chinese did this. Maybe it's because of liberalization, maybe it's because of trade opportunities, but in any case, it's certainly consistent with this picture. The economy at K star is no longer in equilibrium. K grows to K star prime, and the implied input to production leads to Y star prime. Okay? So what we see is a succession of small steps. In fact, if you're interested in mathematics, an infinitely large number of small steps that get increasingly small. Asymptotically, we will approach the new point. You can get arbitrarily close. Okay? So it's interesting. Most important distance will be covered in the first few years of this process, obviously. Okay? There's definitely a correlation in the data between investment rates and growth. Okay? So this is, if you look carefully, you see that there are points of different color, and these different colors also are not accidental. So the red dots are European countries, and you see a much stronger positive correlation there. You also see some countries that are obviously growing despite very little GDP investment per capita. This is over a longer period, so this can be seen as kind of subsuming a lot of other things, political changes. You know, if you move from a very repressive anti-market regime to one in which markets can function, you'll certainly get some growth for free at a given capital stock per capita. Okay, more interesting maybe are the African countries, some of which have invested a lot and have not produced too much growth. And at the same time, you wonder if that's also not having to do with the production function. So again, restricting our attention to countries that have a similar sort of production technology, you definitely see a positive relationship. So along the rate, along this path, you'll see increasing investment rates and increasing GDP per capita. At the same time, it's important to understand that this model does not predict that countries that invest a lot, grow forever or grow faster forever. This model is about comparing steady states of output per capita. We don't have the machinery yet to predict a relationship between investment and the growth rate in the long run. The evidence for that is less strong than it is for countries that invest a lot, have high standards of living. Countries that invest a lot tend to grow along some dynamic path at a faster rate. Now, this model is great, and you've already taken Makro 1 and 2, so you already know this in principle. You can extend this model in a number of different directions and get even more explanatory power and raise even more interesting questions. That's what we're going to do today. We're going to apply this to the regional convergence of two geographically located parts of the world, approximately neighbors, if you like, and looking at just the rate at which they converge if you didn't allow them to interact in any way except to share the same interest rate, the same external conditions. Okay? Let me tell you why the Solow model in its simple form is still kind of unsatisfactory. One reason is that growth in GDP only derives from growth in population. We know that's not a perfect correlation. We know there are a lot of African countries that have high growth rates of population and are not growing very fast, but we also know there are countries that have little population growth and they're also growing fast. So you have to add some extra bells and whistles to get this model to function better. To do that, the simplest way to do that is to let capital A change in the production function. Let the effectiveness of labor in the production function change over time. Okay, so this is what we call the Harrod-neutral model of technological progress. This is basically like saying that if over time our labor learns how to work with capital and become more effective, as if that labor were just cloning. Okay, it's one way of thinking about it. It's like I have Frau Keidel, my secretary. It's like next year I have two Frau Keidel, working with the same computer. She's just much more effective because she's learned, if you like, or she's adapted her work style to adapt to the capital stock that she has. This is a fairly good model of thinking about the way economic relations evolve over time from the technology side. Okay, because it has certain predictions we can go into later about the share of GDP in the steady state, in a state in which the ratio of capital to output is actually constant. And under those conditions, Harrod-neutral technical progress is the right way to do it. There are other ways. Okay, so some of you may be familiar with this. The classic that people always talk about is if you like, the Hicks-neutral vision, which says that basically the production function is shifting out in a homothetic way. Okay, or the isoquant, if you like, is shifting in a homothetic way, not favoring either labor or capital. Or you can think of Solow neutral technical progress, which would be like making capital more effective. Think of Moore's law maybe, or something like that. There are different views on this. People who do growth theory tend to believe that over the 20 decades that we've seen economic progress, Harrod neutral is probably the most robust way of thinking about it, but there have been times when Solow neutral technical progress is a pretty good way of thinking about the world. We'll stick with Harrod neutral technical progress. Okay? So if you do that, we can do the same constant returns to scale exercise, except now we don't divide by L, we divide by AL. And think of AL as effective labor, labor measured in efficiency units. Okay? So what does that mean? That means it's a measurement trick, okay, to account for labor's effectiveness by just measuring labor that way. It's as if you worked 15 hours, you only worked 10, but you're just more effective. Okay? So we're going to take that type of technical progress as exogenous. We're going to assume that it grows exponentially at rate little a, starting from some initial condition. And then we can let our theory do its magic. It turns out that everything is just a transformation of what we did before. It works beautifully. Okay? The intensive form even has the same form. We make A disappear by dividing left and right by A times L. So output is measured output per units of effective labor, or inefficiency labor terms. Capital is measured in the same way. Investment, similarly. Okay? Everything we've done until now goes through, except the interpretation of the outcome is different. Very important. And since you're advanced bachelors, I'd expect you to understand this model. Okay? Because it's more refined. It's a bit more clever. It allows for per capita GDP growth in the steady state. In a sort of a stationary state in which the grand ratio of capital to output is constant, we can have per capita growth and a constant labor share. Okay? There's the picture of the extended Solow model, extended to include labor augmenting technical progress. It's a fairly straightforward enterprise. We can do all the comparative statics before, except a lot of people trip up on this. What happens if little a increases? What if the rate of growth of technological change changes? And I'll let you do that in the section. That's a great question. Doesn't happen very often, but it may happen. Probably happens at a very low frequency. Think about the computer age, what computer age has done for certain types of labor, etc. Let's look quickly at the predictions of the Solow model. The Solow model predicts several things, and several of these things actually are borne out in the data. The limitation of the Solow model, which I should get out there right now, if in case I forget, is that it's very, very poor when it comes to accounting for international differences without adding other production factors. So one of the things we always find is that countries that have low levels of education have low levels of output per capita. That would suggest extending the production function to include human capital. And the education of individuals is like an investment process. Therefore, the obvious extension to this model would be to allow for human capital differences. And as I said before, that can help us explain the differences in per capita GDP between the United States and Niger, but not everything. Okay, so education is important. That's why you're here. To improve your effectiveness in, as well as deepening your intellectual capabilities. So the level of GDP per capita in the Solow model, whether you augment it or not for technical progress, is able to create a fairly robust prediction on the relationship between the level and the rate of savings and the level of per capita output. It's also going to predict relations with the growth of technical progress, little a, the depreciation rate, and the population growth rate. Now, if you read a Makro textbook in a bachelor program, you'll see these predictions documented with pictures, maybe even regression analysis. There's a very famous paper by Greg Mankiw and co-authors where they are able to explain quite a bit of the variability of output per capita just by appealing to some of these terms, including investment in human capital. So in their model, this is a very important paper that looks at human capital as well as physical capital. However, the Solow model does not predict differences in GDP per capita growth in the long run. The idea is there's a frontier of knowledge, and if you take the Harrod neutral approach, then the rate of growth of labor augmenting technical progress is little a, it's exogenous. It may be given by inventions or maybe the long-term investment in universities and research facilities, but ultimately it's not predicted by the model. It's an exogenous factor. And in the end, the Solow model does not touch that one. It doesn't really predict where that comes from. There are many interesting papers in growth theory that do deal with the sources of this type of technological progress. For us, it's exogenous. And obviously you need it. You need A positive to get something interesting in the data. Now, if you look at the data, if you remember my macro course, I showed a very interesting picture for GDP per capita in Germany, France, and the UK since 1850. And we get incredibly robust predictions, even despite world wars and financial crises. GDP per capita has grown at a fairly stable rate, about 1% in these countries, 1 to 1.5%. You know, even though Germany lost a lot of capital, human and physical capital in World War II, has still come back to this growth rate. Third prediction is the adjustment rule. This is where it becomes relevant for our analysis in this course. So the growth that the Solow model predicts the best actually is the growth rate along the adjustment. Okay, so think of the adjustment path we had before. You're starting at some inferior level of capital per capita. The model predicts there's going to be gross investment that exceeds the necessary investment to keep capital stable, so capital starts to grow. We move to the right. That growth will slow down over time, okay? And it's a monotonic rate, a monotonically declining rate of growth. It's interesting to ask the question, how long does it take, using the predictions of the Solow model, for this growth to occur? So I'm going to go about it in a different way. I'm going to ask, what does the data tell us about regions that have similar economic conditions, similar rules of law, similar production functions, and how long does it take for those to converge? So there's a very famous paper that is still the benchmark in this area by Robert Barrow and Xavier Solow-Martin in 1990, looking at the growth rate of American states. Now that's a great example of an economic experiment, right? You've got the United States, you've got 50 jurisdictions, even 51 if you consider Washington, D.C. We have very good data. We don't necessarily have GDP data for all the years, but we have gross net state income, and we have GDP in the last 50 years. We can look at the rate at which those guys converge. So you could think of the initial conditions of the U.S. South would have been different from those of the rich North. And because of the Civil War, maybe things got even knocked off, further off path. Sounds like Europe. You've got Greece, you've got Italy, you've got Spain, you've got Germany, Denmark. They're all different initial conditions. And, well, Barrow, Solow-Martin run regressions. I'll show you some of that evidence. They show fairly convincingly that the unconditional expectation of convergence, or conditioning only on the initial condition, is 2% per year. So 2% of the gap between the richest state and the poorest state will close every year. 2% is not very much. Okay, and we'll show some evidence in a second. Now, I want you to learn something for this course that's very important, which is the doubling rule. You can also think of it as the Halflife rule. And if you want to be a consultant at McKinsey, it's usually useful to have this because you might impress a lot of people by knowing how to throw this out. So if something is growing at 5%, how long does it take for it to double in size? You've been smiling the whole time. Why don't you tell me what it is? What's the answer? No, this guy. You, yeah.
But it's exponential, so it should be very fast.
That's a McKinsey answer. Give me a precise answer. How many years will it take, if I'm growing in size at 5% per year, how long will it take before I'm twice as big as I am right now? Yeah. 13? Actually a little bit longer. The rule is 70 divided by the growth rate. Okay, 770 divided by the growth rate. That's an iron rule, you should learn it. Okay, so the answer is what? Well, somewhere between 14 and 15 maybe? You're going to tell me the exact answer? So you have to divide, okay? So this is a fairly common way of dealing. It also goes in the other direction. So if something is shrinking at the rate of 15% per year or 5% per year, okay? So it's 70 divided by 5, 14, okay? You with me on that? So it applies to doubling as well as halving. So if you have a 2% convergence, how long will it take to cut the difference between GDP per capita in half? 35 years. It's an approximate result. It involves a logarithm of 2, okay? So that's a long time, 35 years. So let's look at the evidence and see if we can convince ourselves. That's kind of the extreme bound on outcomes. We're going to look at the United States since 1880. We're going to look at Europe since 1950. We're going to look at East Germany since 1990. Now, I'm not saying this is an iron rule, but it's certainly a fairly robust rule. It's something that people have to worry about. So Professor Barrow, very famous Harvard economist, basically stuck his neck out, stuck his head out the window and said, basically, it's going to take 35 years for East Germany to converge to West Germany. That was a fairly courageous thing to do. Some would say maybe a bit reckless. The gap has been closed more rapidly. But certainly in most cases, and he's using a wealth of studies that he has done, published in very, very good journals, that have shown exactly this. It's about 2% per year in the United States, okay? And again, abstracting from capital mobility, which should actually accelerate the process. Capital mobility should increase the convergence rate. Okay? Labor mobility should also increase the convergence rate. So think of this. This is a plot of annual growth average between 1880 and 1988. And this is the initial condition in 1880, the logarithm of GDP per person, here, per capita personal income. So they didn't have GDP statistics in the 1880s. They had income statistics. So you can see that the rich West in the subsequent 100 years grew much more slowly than the poor South, which grew faster. Okay? This is exactly the prediction of the Solow model. When you take the behavior around the steady state, log linearize the model, and compute the growth rate of GDP per capita in that model. You get a rate of growth which is slow. It's actually a little bit faster than 2%, but you can talk about the conditions under which that model gives the right prediction. Okay? This is the 4 regions of the United States. So some might be saying, oh, why you should ever do every state? Okay, we'll do every state, right? We can do that. But let me show you the data first. You can understand where the United States was coming from in 1840. The agricultural South, actually, if you look at that number, it's pretty impressive. 70% of the national average in per capita income in 1840. The Civil War destroyed the South. It's a huge loss of GDP productive capacity for various reasons that I won't go into. New England got richer because of the war, or as a consequence in the process. So the initial condition for the convergence process in 1880 was quite extreme. Huge difference between the northeast, if you like, and the south, agricultural South. So what it meant basically is the South became industrialized. People invested in the South, mostly Southerners. Capital mobility was probably not so high back then as it is now. But over time, you see this convergence process is inexorable, right? I mean, it's quite remarkable. The U.S. South has moved quite high in the rankings, especially the South Atlantic states. The East, South, Central, where I come from, is still not doing so well. But these regional differences resemble Germany or the European Union. Actually, the European Union is more dispersed than this picture. Okay, so they basically run a regression using the states, the 50 states, and they come up with a rate of convergence of 2%. So if you divide 2 into 70, you get 35, predicting 35 years. Okay? There's the states. Okay, so you can see there's a lot of other stuff going on, but still they're hugging that line. The most impressive picture, of course, is the 4 regions, the big regions. And these are not independent observations, obviously, but still, it's a pretty interesting picture. Obviously, the rich western states, which is to a large extent due to mineral endowments, California, Montana, Nevada, have grown more slowly than the poor southern states. As a result, you can see that the trajectory as predicted by the Solow model for the southern states has been the steepest. Okay, so this is, if you like, a year, and here's the log of per capita income on the vertical axis. And you see that there's basically a narrowing of the differences. This is what the convergence idea predicts, but you can see it's a fairly slow process. You can do this for Europe. So each one of the dots in this picture represents a NUTS region. These are regions that are defined by the European Commission, by the European Union as administrative governmental regions, and they're used to collect statistics. Each one of those numbers represents a region. Now, what they've done is they've actually demeaned these regions. So it's a little bit of a cheat, but still very impressive how much convergence you have. So this is relative to the regional means, okay? Now the Solow model mathematically predicts a rate of convergence. So lambda in the Solow model can be thought of as the local behavior of GDP along a convergence path that is given by a set of parameters. So you might want to think about what would happen if I was at K star and I just nudged it a little bit away. How long would it take for me to get back? Okay? The most important fact is that the model predicts that the farther you are away, the faster you will grow initially, and the growth is monotonic. And the way you could derive that is simply look at the expression for Y star in the case of a Cobb-Douglas production function with a constant savings rate, and then log linearize the difference equation for the capital stock around that point. And we know the capital stock is growing if you save more than you depreciate. Okay, so that's going to determine the speed of growth. The initial condition is going to matter as well. I'm not sure we want to do this in section, but I have the handout. I'm not going to do it in class, but we can. It's not that hard. You will do log linearization in other courses. The cool thing is you get this expression, okay, and in most simple models, and they don't even have to be Cobb-Douglas, basically lambda is this expression. It's a function of several important parameters in the model. One, it's a function of the labor share. Alpha is the share of capital in the model, or in the Cobb-Douglas production function, it's the elasticity of output with respect to capital. It's a function of A, which is the exogenous Herod technical progress rate of growth. It's a function of the rate of population growth or labor force growth, N, and it's a function of the depreciation rate. Okay? So around the steady state, that's going to give us approximately what we're looking for. Now, does the model come close to predicting this miserable 2% rate? Okay? So Barrow, being a very honest scientist, said this is a problem. The model predicts much faster convergence than we see in the Solow model. And we see in the data, sorry. So the data gives us this 2%. To get that to be equal to 2%, it's tricky. Okay, so we'll give you some examples. If you think of the labor share as being 1 minus the capital share, okay, so that's means that we're talking about 2/3. 2/3 times 0.01 plus 0.01 plus 0.10 is a pretty big number. It's a huge rate of convergence, very fast. Okay, so something's wrong. Now, how do you reconcile the data? Reconcile the model with the data? Barrow suggested several things. One is to think of a lower depreciation rate. One is to think of human capital as well as physical capital. So in the paper I mentioned by Mankiw, Romer, and Weil in the 1990s, they looked at extending the Solow model to incorporate human capital, investment in education. So you have not only the savings rate of households in physical capital, you have the savings rate of households in human capital. Human capital depreciates. You thought you learned this stuff, but I see a lot of you, wow, Solow, who's that guy? But you learned it last year. You forget, right? That's part of depreciation of human capital. You also may go off and work and not work in economics for a while, and you forget it. Maybe your knowledge becomes obsolescent because Solow's model gets replaced by some other model. These are all reasons that there's a depreciation of human capital as well as physical capital. When you add these features to the model, you can actually get a little bit closer. In that case, the share of capital is more like 2/3, so we can knock down the lambda a little bit. You can also think of the depreciation rate as being lower. You know, this building has been around for 100 years. Now, I just taught you the 70 rule, so now you can figure out how long it would take for a building depreciating at a 2% rate. Okay, we know how long it would take for half of it to fall apart, to be half valued at half of what it was before. So, you know, most of the economy's capital stock is actually buildings, structures, residential and non-residential, and highways. These things take a long time to depreciate. Maybe we need a lower depreciation rate. Still, maybe the Solow model isn't the whole story. Okay, so that's another point to think about. So what else do we have to worry about? Let's go back and look at this picture again. This represents the trajectories of very well-defined regions. These are much bigger than European countries. You know, the Midwest is like Germany and France taken together, maybe, a little bit of Italy. But, you know, European landmass is quite large. We saw that in the first lecture. It's pretty large. The Solow model is assuming that there is no import of capital, that there is no migration. These are very important assumptions, right? So every country, every region is literally pulling itself by its own bootstraps. So if the South grew faster in the Solow world, it meant that the Southerners actually had high savings rates, or you know, were putting aside more of their income at the beginning than they would if they were rich. Okay, that's fine. And we also know why the South is there. If you go back to this picture, to this table, you see that the South was actually quite wealthy in the antebellum years, the years before the Civil War in the United States. This is because the terms of trade for the U.S. South were quite favorable, producing cotton and other tobacco, other types of products that the world wanted, and slavery. For all the abomination that it is actually also an economic fact that contributed to the economic success of that region. So the destruction of the South, the loss of the economic relations that they had, the abolition of slavery, all destroyed, if you like, the productive capacity of the U.S. South. So starting from that low condition, you'd expect this to lead to a sort of an adjustment process that would take many, many decades. Well, this is not an exception. We have shocks like this all the time. Europe is subject constantly to disturbances. Okay, so think of the Greek situation. The Greek economy is subject to a huge demand shock, but it's probably subjected to more than just that. It's subject to an institutional shock. The Italian economy has now faced Chinese competition for 15 years and is suffering because a lot of its industry at the margin can't compete. Okay, Germany had a rough go up until the mid-2000s, competing in the world economy because their labor costs were too high because of unification. So these kinds of shocks put economies away from whatever steady state they were at. So again, you might think that the South, had they operated under different conditions, might be totally in a different place today. And if you look at the US states from year to year, you see that they're subject to lots of different shocks. Some of those shocks involve the government. So in Massachusetts, for example, after the Cold War was over, the US government stopped spending on defense for a while, and that really hammered the local industry in New England. Places in Texas suffered when the price of oil dropped. They're suffering now. Places where fracking is taking place or have lost a lot of business in the past year because the price of oil is so low, and vice versa. So all these are events that happen from time to time that can lead to blips. So this, you think of this as one very large blip. This is the blip of the Civil War. The South should have been there, right? But they're there. These kind of disturbances make us wary of using a concept of convergence that is only based on a deterministic rate of decay, using the 70 divided by percent rule. By the way, that's on the exam for sure, okay? Gregor already knows. I'm going to ask you, how long does it take for something to shrink by half, or maybe even shrink by 75%, because half of half is 25%, okay? So you can use you don't need a calculator to figure that out, right? How long does it take for something to double? Very important. The point I'm trying to make is that we need to adapt our convergence measure to think about this. The world is not smooth. We know from Makro that there's shocks. Think of Greece, think of the financial crisis, think of the sovereign debt crisis in Southern Europe, think of the German unification shock. Some of these shocks are positive. Okay, they can also be negative. Norway, for example, benefiting from the price of oil going up, is a good example of a positive shock. So this means that it's likely that even whether you're at the regional or the national level, that you're going to have variation at any point in time. So that means we have to think hard about this convergence process. It's not just measuring this trajectory, which in the case of the US was pretty smooth, but in fact it's usually not like that. If you take a year-to-year measure, there's a lot of variance. Point-in-time variance is quite high. So you can do this. This is a nice project for someone writing a bachelor thesis, would be actually to calculate the variance as measured as the standard deviation of the GDP or GNI per capita in various states in each year. Now, obviously, that's going to be a very noisy indicator. That's going to be a measure of spread, and over time, these things do change. But at a point in time, you have variance. So you can plot that variance over time. And if you do that, you get a different concept of convergence, which says, okay, we've got a level of disturbances in the economy that we have to recognize as being sort of inherent to the system. And these shocks occur with different probabilities in different regions, and they give rise to a spread over time. And this spread is constant, or it may be declining. Okay, if it's declining, we expect it to decline to some level. And that's kind of what we call sigma convergence. So if you think about this picture now with that in mind, you basically see that the sigma describing the spread of GNI, or personal income per capita, across the US states was very large in the consequence of the Civil War and the economic dislocation that resulted. But since then, since about the 1960s, this spread is fairly constant. It's not getting any smaller. So if you take a deep and hard look at the United States data, you see that there's still a lot of inequality by region, not by individual, but by region. Okay? And these regions tend to flip identity. So the South Central states have done less well, perhaps, as the South Atlantic, which includes Florida. They've had various reasons for being successful. Parts of New England have done very well. Parts of the Midwest have not. Okay, and if you go back to your history, economic history, you know that that part of the United States was quite prosperous 50 years ago. So these things do change over time. This is part of the European story, because as we move into the next section, we're going to start talking about, you know, what are the reasons for these persistent changes? They obviously have to do with economics, but they also have to do with the mobility of capital, mobility of labor. One of the reasons why this has gotten better over time is because the US states don't have to save for each other anymore. They don't have to save for themselves. They can save in a big pool, a global pool of capital, and that pool of capital can be accessible by all states. So the measure of success for the European Union to become like the United States would be to see whether the correlation of investment and savings is still positive or whether it's gone to zero. Because in principle, it should be zero. If you have money and you put it in the bank, your bank should have at its disposal all potential investment projects in the world. It's perhaps a bit broad in terms of perspective, but it could also be all the projects available in Germany or all the projects available somewhere in between in the European Union. And if rule of law is the same, if investors are protected, then a bank should not worry about this too much. Okay, so we'll talk about capital mobility in the next lecture. We'll talk about the details that give rise to a break in this Solow setup. It doesn't necessarily mean that the Solow rate of convergence will be higher, but it's likely to be higher, okay? Which makes it even harder to explain the US data. So we have to think hard about what that means. Capital is not completely mobile. Sometimes too much capital mobility leads to problems. But that's all material for the next section. Okay, so if you look at, you know, if you take a more microeconomic view or microeconomic perspective, you get the same result. This is just to give you a spread. This is the levels. You can see the spread. Spread's falling over time. You can actually measure that spread in each period across the states within the regions and get an idea of how that variance, that within variance is changing over time. So this is an extremely important phenomenon. So even within the West, the dispersion of incomes has gone down. This is the kind of thing we want to look at with the European Union. What kind of measures can be taken? It need not just be capital mobility. It may also be aid, state assistance. The United States is a country, and a country has the possibility of transferring resources. This is personal income. It's not GDP. Okay, so one way of creating this convergence result that we talked about is to actually tax and spend at the federal level. So the US government collects income taxes. These income taxes are progressive. They rise if you make lots of money. So the richest states are paying the most. That's easy to understand. And the poor states are paying the least. So there's an implicit transfer going on. There's also an explicit transfer because the United States has revenue sharing, like the Länderfinanzausgleich in Germany, same idea in the United States. There's also federal funding of certain programs like defense. More importantly than that, there's a number of social programs that are funded at the federal level. And the unemployment insurance system is also funded or refunded at the federal level, even if it's collected and paid out at the state level. So these are other aspects that have to be added to this equation, just to make sure you understand. Okay, so next week, we meet and talk about capital mobility as an alternative to pulling yourself out of the swamp with by your own bootstraps. We'll talk about what leads to capital mobility. We'll talk about the nature of the Edgeworth diagram as a predictor for capital mobility, and we'll talk about how you can model that. Okay, I'll see you next week.